Hello and welcome back to the Free Science Channel Artificial Intelligence Lecture Series. In this video, I'm going to teach part 2 of Recurrent Neural Network Architecture, which is the advanced section in Artificial Intelligence Lecture Series. I hope you enjoyed part 1 of the Recurrent Neural Network Architecture. And as I said before, a solid understanding of the deep learning is a prerequisite of this course. I'm going to turn off the camera and start teaching. Let's start by the learning outcomes of this video. From first video, remember you have learned vanilla recurrent neural network, which was the simplest architecture of the recurrent neural network. In this video, first I will start by describing multi-layer recurrent neural network and bidirectional recurrent neural network, which are a bit more complex than vanilla one. Then I will discuss the training of the recurrent neural networks using backpropagation through time, BPTT method, and the challenges that we will encounter during the training of the recurrent neural network, and also with some mathematic insights of the issue. And then the solutions that we have to cope with these challenges will be introduced, how to get rid of the challenges that we will encounter during the training of the recurrent neural networks. And then I will introduce long short-term memory LSTM network, which is one of the solutions or new architecture, which is introduced to get rid of the challenges of the recurrent neural networks, and then gated recurrent unit, GRU networks. Okay, here in the right side, the graph shows the multi-layer recurrent neural network. We can add more complexity to the recurrent neural network by extending them along the depth, vertical extension, and along the time step, a horizontal extension. The important thing is when we are extending along the length, each layer itself is one recurrent neural network that receives the input from the previous layer and deliver the output to the next layer. This one, for example. And the idea of adding more complexity to the recurrent neural networks is to learning more complex pattern. But the study shows that when vertically we extend the recurrent neural network, the lower layer, the lower neurons at the lower layers learn fast changing features, and the upper neurons at the upper layers learn abstract features. That's why the values of neurons at the lower levels will change more repeatedly compared with the upper layers. Generally, we prefer to not have more than 2 to 3 layers in recurrent neural networks. But extending the recurrent neural networks, adding complexity horizontally along the time steps is a thing that we like. Yeah, we like it, and because it can capture more interesting features. The next item is the next complex configuration for architecture is bidirectional recurrent neural network. The interesting thing about bidirectional is if we couple two recurrent neural network, one forward, one reverse. Here we are moving from input to output, and in the reverse form we move from output to input. If we couple these two, if we then we will get bidirectional. The important point in this architecture is each output, like YT here, receives input from the forward network and backward network both. You remember from the vanilla recurrent neural network that hidden state, the hidden state vector had a formulation like this. For forward and reverse, we can write the same, but that's the point. HLT here is just hidden state and hidden vector of the forward. That's why I use different weights. I use prime for the reverse one and W for the forward one. This means that necessarily the weights should not be equal. And to show the total hidden layer, we should concatenate the HLT and HL prime T. And output simply is written here. We have an activation function. Alpha is activation function. And HT is from this formula. That's concatenation of forward and backward hidden state. And we have a bias. Typically, these models, these networks, are used in speech recognition. Okay. Now, the question is, when we have a recurrent neural network, how we train our model? You know that training is optimization model. You should calculate a loss and then move forward, backward and try to minimize the loss as much as possible. The first step is just whatever we were doing for neural networks, for fully connected neural networks, we should do it here. Therefore, the first step is unrolling the recurrent neural network. Here is a closed form of recurrent neural network. We have three weights, sorry. WIH connects the input to hidden state, WHH connects the hidden states together, and WIH connects the hidden state to the output. If we unroll the closed form of the recurrent neural network, we get something like what we have here. Okay, after unrolling, as we had in neural networks, in fully connected neural network, first we should move forward and perform forward propagation. With forward propagation, we move from the input, which is here, to the output. And finally, we will calculate one loss. This loss will be summation of the species of loss, because we will have one loss from here, one loss for YT, and for other outputs also. We will calculate one output and total loss, and then we should update our parameters. To update our parameters, we should go for backpropagation. Backpropagation through the time. Okay, moving from the loss toward the parameters and calculate the partial derivatives. All of our weights should be updated. We have weights WYH here, WHH here, which connects the hidden states, and WIH. To calculate the partial derivatives and minimize the loss value as much as possible, The main core here is chain rule that you have learned it in mathematics. We start by partial derivative of total loss with respect to output, then output with respect to hidden state, and then hidden state with respect to recurrent weight matrix. But here for brevity, I just showed the WHH. This fraction should be written for all of the weights like WIH, WHY, and WHH for all of them, for all three introduced weights in recurrent neural network. After third stage, which is backpropagation, we will have one fraction which is a bit challenging, which gives us a Jacobi matrix here. And the reason is we have multiple layers, multiple repeated layers, like HT minus 1, HT plus 1, HT plus 2. And because of that, this fraction, calculation of this fraction can be a challenging for training of the recurrent neural network. I will back to this gray box here in the future slides. And the next step is updating. The next step of training course is updating the weights. For updating the weights, we should, after calculation of this fraction, we will multiply it by layering rate and subtract this value from old parameter value, old weight value, to calculate the new weight values. These 4 steps are how we train all type of the networks, including recurrent neural networks. Get back to the challenge that I mentioned in the previous slide. We may have exploding or vanishing gradients when we are training the recurrent neural networks. Here, I want to just give you an intuitive example, and then I will go through the mathematical insights. For vanishing, if we have a value like x between 0 and 1, and we multiply it by itself multiple times, then we will diverge to a very small value, like very low, we get very close to 0. And if we have a value larger than 1, and if we multiply it by itself over and over, finally we get very large value. We diverge to the infinity. It is a main idea. And then if we get vanishing, if we have vanishing gradients and have parameters very close to 0, this may slow down the learning and stop the training. And the same for the exploding gradients. When parameters diverge to infinity, it will cause the learning process to fail. That's why we should avoid to have exploding and vanishing gradients. This was just an intuitive example, but about the mathematical insights, you remember this fraction from a previous slide, and this bracket that in previous slide showed with the gray box. This bracket, in fact, is a Jacobi matrix, and to calculate this bracket, we need a functionality. We need a functionality between the h and ht minus 1. Here, the function is introduced, the hidden state, the hidden function is introduced here. Let's calculate the derivative of ht with respect to dht minus 1. If we have such a function and we want to calculate this fraction, the first item will go to 0 because there is no dependency to the dht minus 1, and this one will go to 0, and we'll end up with just this parameter, and we will get WHH sigma prime. Yeah, sigma prime. First derivative of the activation function. You see here the Jacobi matrix, is shown with a product. This means that repeatedly we should calculate each fraction and multiply them by together. If we do so, finally we will have one recurrent weight matrix, which is timed by itself several times, and activation functions that they will be multiplied by itself multiple times. But how can we estimate this product? You should have a solution, you should have a method to mathematically estimate or predict this product. Otherwise, we cannot judge that we will have vanishing or exploding gradients. You remember from the linear algebra that when we had a Jacobi matrix like this fraction, this hi and h minus 1, and you wanted to we had a Jacobi matrix, and we had this formula that the spectral norm of the Jacobi matrix equals to the spectral norm of the linear part multiplied by the spectral norm of the nonlinear part. If we show the hidden state by this function, the nonlinear part will be activation function, and the linear part, will be recurrent weight matrix. Okay, but our problem, you remember from the previous slide, here we had a product form. We should show our problem with a product form. Then we should adopt this linear algebra formula to our own problem. Here I added the product to all of the items. The product of this Jacobi matrix equals the product of the nonlinear part, nonlinear operator, and the product of linear operator and product of nonlinear operator. Yeah, the spectral norms also are shown with these parallel lines here. They are spectral norms. This diag here means diagonal matrix, and it will give us a matrix like this, a matrix that along the diagonal we have the derivative of the activation functions. Okay. Therefore, to calculate this fraction that we should calculate it during the backpropagation, we need to know every single of these products finally will end up to which value. At least estimate the how small it is or how big it is. To do so, I will discuss the activation function and recurrent weight matrix separately. First, let's start by activation function. You know that the activation functions are functions which are continuous, derivable, and if we calculate the derivative of activation function, if we get a value less than 1, we will have vanishing gradients. And an intuitive example here is, for example, if we get half out of the activation function within 10 layers, if you times 0.5 10 times by itself, you will get very small value here. That therefore our parameters will get very small parameters, and it will slow down the learning of the network and finally stop the training. Conversely, if we get values larger than 1 from activation function, you will have exploding gradients, and it will cause failing we will our training course also will be failed if we get exploding gradients. The intuitive example is 1.5. If we time it by itself 10 times, we'll get very large value. Let's review some real examples from activation function. Here is a tangent hyperbolic. The blue curve is a tangent hyperbolic. The purple one is its derivative. You see that we have an upper bound for derivative of tangent hyperbolic. Therefore, any tangent hyperbolic, if we calculate the derivative of tangent hyperbolic, values will be between 0 and 1. Any value we put in a tangent hyperbolic, we should get, if you put x here, let me correct it. Yeah. Any derivative gives us value between 0 and 1. Therefore, it is probable to get vanishing gradient, but not exploding gradients, because the top value is 1. And if we multiply 1 by each other 1 million times, still the result is 1. The next example is sigmoid function. The blue curve is sigmoid and the orange curve is its derivative. You see that the derivative of the sigmoid function sigmoid x is between is less than 0.25 maybe, yeah. And it is probable, by using the sigmoid function, it's probable to get vanishing gradients, but not exploding gradients, because upper bound is 0.25. Comparing the tangent hyperbolic and sigmoid function, if we have if we compare them together, we see that the if we select the sigmoid function for a recurrent neural network, we will reach to vanishing gradients earlier than tangent hyperbolics, because with tangent hyperbolics we can get larger values like 0.8, 0.9, while we cannot have these values with sigmoid. That's why in recurrent neural networks we use tangent hyperbolics as a activation function. The next example here is ReLU, and the red curve is ReLU and the green is its derivative. As you see here, the derivative of the ReLU for values less than 0 is 0. If x less than 0, it would be 0, derivative of ReLU. And if x is larger than 0, the derivative of ReLU will be equal to 1. For values less than 0, for sure we will have vanishing gradient, but for x larger than 0, greater than 0, we will not have exploding gradients. There are some examples that that I just want to show intuitively. If we select different situation functions, what will we get at the end? Okay. The next item is recurrent weight matrix. You remember when you wanted to calculate the partial derivative of loss with respect to partial derivative of the recurrent weight matrix, we said the spectral norm of this value is proportional by a spectral norm of h I minus 1 to h I, and this is less equal than a spectral norm of, we had a product here, WHH transpose, times a spectral norm of, again we had a product here, a spectral norm of, this is the product, these two are pi, they're product of diag sigma prime. We discussed the activation function, about the boundaries and how activation function value will affect the vanishing and exploding gradients. And now I want to discuss WHH. Again, from linear algebra, you remember, if you show the eigenvalues of WHH with lambda 1, lambda 2, lambda 3, the maximum absolute eigenvalue will be the spectral radius of WHH. If the spectral radius, if you have a spectral radius of a spectral radius which is less than 1, and multiply WHH by itself multiple times, we will move towards 0. And if you have a spectral value of which is greater than 1 and multiply WHH by itself multiple times, and we will move toward a big number or infinity. Therefore, vanishing and exploding, we have learned vanishing and exploding gradients are common challenges of recurrent neural networks, and but there are solutions. There are solutions. We have methods and tricks to get rid of vanishing and exploding gradients. For exploding gradients, we can use clipping, gradient clipping by value. And the idea is if we show the gradients, one gradients like g, lowercase g, and we see that the lowercase g exceed from the certain threshold that we defined, then we can reset the g by the value of the threshold. There is another method. This is called clipping by norm. This is more general than the first, I think, but they're very similar to the first method. Here, instead of one gradients, we have vector of the gradients, which is shown by omega. And then we should calculate the L2 norm of the omega and see if it exceeds then a certain threshold that we define, then we should rescale each gradient by this formula. And this formula says just time each species of the gradients by this fraction. This fraction is threshold divided by norm 2 of the omega. Omega is a gradient vector. The first and second method is useful to avoid exploding gradient, but the third method is used to avoid vanishing gradients. If we initialize, when we start a training, initialize our parameters with identity matrix, then we will get when we want to calculate the partial derivative of L with respect to partial derivative of recurrent weight matrix, we will have just one which is multiplied by itself over and over, and it will help us to avoid vanishing gradients at the beginning of the training. But when weights are updated, I showed that when we calculate the new weights by there's no guarantee that the identity matrix remain the eigenvalues remain 1. The entity of this matrix remain 1. They may change. But if this method is useful just for a starter training, and we can make sure that at beginning of the training we will not have vanishing gradients. But a robust method to avoid vanishing gradients is changing the architecture. Here, I will introduce LSTM architecture, which is designed to alleviate vanishing exploding gradients by maintaining the cell state and using the gating method. By gating, this means that controlling the flow of the information into the neural unit and select which information we keep or which information which is not or unimportant or filter out unimportant information. It is the main concept of LSTM. But how these gates are defined, the original form of LSTM includes input gate, update gate, and output gate. As you see here, these gates are introduced here in the graph in the yellow box at the bottom right. It is input gate, update gate, and output gate. And how mathematically we can show that we can avoid vanishing excluding gradients. Just we need to have a cell state. Cell state in LSTM is shown by CT equals to CT minus 1 plus input gate dot GT. And the output also is shown by this. You remember from the backpropagation that we discussed it earlier, we have to calculate the partial derivative of loss with respect to hidden states. And because of the chain rule that we had, if you look at here, this yellow box shows exactly the mathematical insight of the LSTM, how LSTM can, by LSTM we can avoid the vanishing or exploding gradients. If we show the cell state by C, when we want to calculate the partial derivative of L with respect to CK, for first and second fraction is a usual partial derivative calculation. The rest from here after, we will see a Jacobi matrix again. If we, given that we have this function for CT, if we calculate the derivative of CT with respect to CT minus 1, we will see that we'll get 1. And then we have several ones, multiple ones, which are going to be multiplied by each other, and we will not have exploding or vanishing gradients. But this is the original LSTM, the first LSTM architecture which is introduced. The standard LSTM today has a forget gate also. By input gate, we'll decide how much information we want to input to our network. And by forget, it will decide how much of the old information should be forgotten. They are important and we want to filter it out. And by output also, the network decides how much of the information network should reveal. Just the difference of the standard formulation of LSTM with the original one is for cell state, we'll have this multiplication, this dot product here between FT and CT this one. This means that if we calculate the derivative of the CT with respect to CT minus 1, again, we will have FT prime. It will depend on the value of the FT. FT is important here. Or if we see here FT sigmoid, we can avoid FT prime. We just show it with FT because it's, FT is output of the sigmoid. Yeah, we see that here the result of the partial derivative of L to partial derivative of C will depend on the FT value. This shows that there is a potential to have vanishing gradients with the standard formulation, but there is a solution for it. If even we get a vanishing gradient, it is not that much extreme as we had in RNN, as a vanishing problem that we had RNN. The solution for it is when we start the training, we can select the biases with positive large values larger than 1, values which are positive and larger than 1. This will lead to have a sigmoid of a large value inside the bracket, and finally we'll get ft equals to 1. Ft equals to 1 means forget gate remains open at the beginning of the training course. But it doesn't matter. We start by large values of PF and avoid vanishing gradients, and then model over time. We learn to forget which part of the information and filter it out, and maintain which part of the information. Yeah. Therefore, the solution to avoid the vanishing gradients is when we start the training, we select biases larger than 1. The other variant of the LSTM is Gated Recurrent Unit, GRU network. In the GRU network, in fact, the input gate and forget gates are kind of merged, and the cell state and hidden state are merged. And in GRU, we have an update gate that determines how much past info is carried forward to the future. Update gate will let us to know how much information should transfer for the future. And we have a reset gate, which controls how much of the past information should be omitted. And the current memory, which is shown by GT, and final output, which is shown by HT. Here, in the yellow box, you can see the reset gate and update gate, which is shown here, and finally output and current state of the memory. Therefore, using different architectures, making change in the architecture of RNN and using LSTM and GRU is another robust method to avoid vanishing and exploding gradients. Let's wrap up the RNN. So far, within 2 videos, we discussed the recurrent neural networks. First, we started by sequential data, and we discussed how using sequential data, inputting sequential data to neural networks and convolutional neural networks is challenging. And the challenges, if you remember, were first of all, we need for NN and CNN, we need a fixed input length. And in neural networks, parameters are not transferable, although in CNN parameters are transferable, but still in CNN we need a fixed length of the input, and high computational cost was another problem that led us to think architecture can handle sequential data. This architecture is recurrent neural network. First, we introduced vanilla recurrent neural network in the first video. The closed form, if you remember, was RNN, and we had the output going with YT. We had the input XD, and we had a hidden states, multiple hidden states. And then when we unroll this box, we would get multiple hidden states. It was a vanilla form of the recurrent neural network. And in the second video, we introduced multiple layer. We said, as you remember, we can couple several layers of recurrent neural network along the depth or time step and add more complexity to the network. But we avoid exceeding from 2 to 3 layers along the depth. And we discussed that you would like to have more layers along the time step to capture more interesting features along the time step. And we introduced a bidirectional one, just if you couple one forward and one reverse recurrent neural network, we would get one bidirectional one. And the important one there was the total hidden state. Would to have the total hidden state, we should concatenate the HL and HL prime. HL prime was hidden state of the reverse network, and HL was hidden state or hidden vector of the forward network. We discussed a bit the mathematical insights of the training recurrent neural networks and the challenges that we encountered during the training. And the challenge was vanishing and exploiting gradients. And we introduced some solutions. One solution was clipping the gradients by value. And clipping the gradient. The other method was clipping the gradients by norm. These two methods were used for are used for avoiding exploding gradients. And also we can use the identity matrix at the beginning of the training for recurrent weight matrix to avoid vanishing gradients. But none of them is a robust solution. A robust solution to avoid vanishing and exploding gradients is changing the architecture of recurrent neural network. And we introduced the original recurrent neural network, which had a input gate, update gate, and output gate. And you remember the mathematical insight also discussed how using the LSTM could avoid vanishing, and using the original LSTM could avoid vanishing and exploiting gradients. But the standard configuration, standard architecture of LSTM also has a gate which is called four-gate gate. The LSTM have control on inputting the information to the network and outputting the information from the network, and also has the ability to forget part of the information that are not important. And this control on information flow makes the LSTM interesting network. But a standard one, in a standard form configuration of LSTM, it is probable to have vanishing gradients. But still there's a solution for it. We advised at the beginning of the training, we select the biases larger than 1 to have a sigmoid equal to have a FT equal to 1 at the beginning of the training. It means that we're keeping the forget gate open at the beginning of the training, and then over time the model learns which information should be forgotten and which information are unimportant and should be excluded from the input. And finally, we introduce another variant of the LSTM that merges input and forget gates. Also merges the state cell and hidden state that we have in LSTM. It's a bit different configuration, the same concept more or less, but different configuration. And this method also is useful to avoid vanishing and exploding gradients. Here is the end of the recurrent neural network course.